Today, we're starting a discussion about agents and software transactional memory. We'll explore how agents, which can be thought of as independent units of computation, work alongside software transactional memory, a technique that helps manage shared memory and concurrent programming. This approach makes it easier to write systems where multiple processes operate together without causing conflicts or errors. Throughout the presentation, I'll explain these concepts step by step, helping you understand how they improve software performance and reliability. Agents allow state changes to happen independently and asynchronously, meaning they don't block other operations while updating. These updates are made by sending functions to the agent, which then processes them one at a time in order using a thread pool. This ensures changes happen sequentially without conflicts, making it easier to manage state safely in concurrent environments. Agents operate using asynchronous message passing, which means they communicate by sending messages without waiting for an immediate response. Their consistency model is eventually consistent, so while updates may not be instantaneously reflected, they will converge over time. Each agent guarantees the order of messages it processes, ensuring messages are handled sequentially per agent. Additionally, sending messages is non-blocking for the sender, allowing other processes to continue without delay while the message is being handled. In Clojure, mutable variables include agents and refs, which, like atoms, are designed to handle concurrency. These types work closely with persistent data structures to keep identity and state separate, ensuring reliable state management across different threads or processes. Agents provide asynchronous updates by processing functions sequentially, while refs allow coordinated, synchronous state changes within transactions. Together, they help manage state changes smoothly and safely in concurrent environments, offering different approaches depending on whether you need independent or coordinated updates. An agent works much like an atom by holding a reference to a single value, allowing that value to be accessed when needed. You can retrieve this value using deref or the shortcut symbol @. For example, when we define an agent starting with the value of 0, we can access that initial state simply by dereferencing the agent, which returns 0. This encapsulation provides a clean way to manage state within agents while maintaining clear and consistent access to the stored value. When you want to change the value of an agent, you do so by calling the send function with the agent and the function to apply. For example, sending the increment function increases the agent's state by 1. If you check the agent's value using the dereference operator, you'll see the updated value. You can also send arithmetic functions with arguments, like adding 2 to the current value. Even though the send call returns immediately with the agent itself, the actual value inside the agent updates asynchronously and can later be accessed by dereferencing the agent. This shows how agents manage their state independently by applying changes through functions sent to them. Send works like swap, in that it takes a function and optional arguments and applies that function to the agent's current state, with the new state being the function's return value. The main difference is that send returns immediately without waiting for the state to update because the function runs asynchronously later. When multiple threads call send on the same agent at the same time, those functions execute one after another, not concurrently, so only one runs at a time. Because of this sequential execution and lack of retries, functions sent this way can safely perform side effects without worrying about being run multiple times. Agents are commonly used in situations where you need to perform tasks asynchronously without blocking the main flow. For example, logging is a great fit because you want to record events without slowing down other operations. Background computation is another typical use, where agents can handle work that runs independently of user interactions, freeing up resources in the foreground. They are also well suited for maintaining counters or gathering statistics, where updates can happen concurrently without interfering with each other. Finally, agents can manage independent services that operate parallel to the primary system, keeping processes isolated but coordinated. These use cases highlight how agents provide a flexible way to manage state changes and tasks in an asynchronous, non-blocking manner. When we compare swap and send, the key difference lies in how they handle updates. Swap works with atoms by performing updates synchronously and atomically, which means the change happens immediately and is guaranteed to be consistent. Plus, swap can retry if there's a conflict, ensuring the update goes through correctly. On the other hand, send operates on agents by scheduling updates asynchronously. These updates are serialized so they happen in order, but they're not retriable, meaning if something goes wrong, the system doesn't automatically try again. This distinction makes swap Ideal for cases where immediate consistency and retry capability are important, while send is better suited for background processing that can run independently without blocking the main flow. When using swap, the function is applied immediately to update the atom's value, and if another thread changes the atom at the same time, swap may retry the update. Because of this, the function must be pure without side effects, since those side effects could run multiple times. On the other hand, send works differently by queuing the function to run later on an agent's state. It executes the function exactly once and ensures that all functions are run in order, one after the other. This means side effects are allowed when using send because the function won't be retried. This distinction helps determine when to use swap for immediate, atomic updates and when to prefer send for serialized, asynchronous tasks with side effects. When multiple threads try to update using swap, they do so concurrently, meaning updates can happen at the same time. The process relies on compare and swap, or CAS, which means that if two threads conflict, one may need to retry its update. One important thing to note is that swap does not guarantee the order of updates across different threads. On the other hand, with send, multiple threads can enqueue actions at the same time, but the actual execution happens sequentially. This means only one action runs at a time for each agent, and the order in which actions are queued is preserved. So, while swap allows immediate but potentially conflicting updates, send ensures that actions are orderly and serialized for consistent state changes. When deciding whether to use swap or agents, consider the nature of the state and the kind of work involved. Use swap when the state is independent, updates are fast, pure, and require immediate consistency without side effects. This is ideal for things like counters, caches, or configuration flags where you need synchronous, atomic updates. On the other hand, use agents when the work should be asynchronous, updates need to be serialized, and side effects are necessary. Agents are suitable when the caller must not be blocked, such as during logging, tracking metrics, or running background tasks. This distinction helps ensure that your code remains responsive and correct depending on the requirements.